Now we have external agents that can cause, these are the inducible mutations. Okay, we talked about the spontaneous mutations. Now, what are they? You have what? Deamination, depurination. What else? Spontaneous. You have the tautomeric shifts. You have transposons, the oxidative stress. Those are all spontaneous mutations. Now, looking at induced mutations, inducible damage, you have the ones that are the most drastic are the base analogs. So those are used very commonly for the treatment of cancer. Why? Because these base analogs will resemble the normal nucleotides. They will look just like the other ones, but they are going to cause a severe change in the DNA structure. They are going to stop polymerase from polymerizing, from doing the replication. So if that happens, the cell dies. Now, you have in mind that cancer cells are replicating at a very fast pace. That's why they are cancer cells. The control of their cell division is totally dysregulated. Now, if you add base analogs to these cancer cells that are replicating very quickly, those analogs are going to be stuck on the DNA that is supposed to be replicating. Now, DNA polymerase is going to get in there and it's going to fall off because it does not recognize what in this world 5-PU is not any base that it has encountered before, so it does not replicate. It just gets stuck over there and the cell will die. If you can do that only to cancer cells, you will be great. Now remember that you have other cells that are constantly dividing in the body, like for example hair. So when you have base analogs that are being injected in your veins for treatment of cancer, is not only going to kill some of the cancer cells, it's going to also make your hair fall out, because the hair cells are just not going to be able to divide. They are going to try to divide, and then those analogs get in between, and oh well, more hair. But eventually with the hair cells, once you stop the chemotherapy treatment, the hair cells will recover, and eventually the person will get hair again.
Is that all hair everywhere, or just the hair?
What do you think? Is everywhere hair growing? Yes, so the person doesn't have to shave for a long time. This is one base analog or intercalating substance. That what does this do? It does the same type of job as a base analog would do. It gets in the middle of DNA and causes a lot of damage, a lot of mutation. Those are alkylating agents. And what happens? It will get stuck in the middle of the DNA and will totally mess up gene expression. Yes?
Back to what you were talking about before with the hair. There's patients who lose their lashes.
Oh yeah, all the hair that is dividing. Oh yeah. The eyelashes, the eyebrows, and yeah. Well, I'm not sure the patient will be very happy with the thicker and bigger eyebrows. Oh yes, I mean armpit hair, leg hair, everywhere else hair, it just falls off. Okay, so coming here to our alkylating agents, those have groups that will cause abnormal base pairing. Again, it's going to intercalate, it's going to get in the middle of the DNA and it's going to mess up gene expression. One example that I had mentioned many times is ethidium bromide. Gets in the middle of the DNA. This is how actually we can see the DNA in the gel, because ethidium bromide will get in the middle of the DNA. So then it will shine. Now, ethidium bromide can cause this type of mutation, and also one agent that was widely used during World War I is mustard gas. This is the structure for mustard gas. Everybody heard of mustard gas before?
Yes.
Yes?
No.
Chemical agent, World War I. This is how they would kill. I don't know which side was attacking with the mustard gas, but they would kill all the soldiers that were not using a gas mask. Once it gets into your system, you start to basically have the same type of phenotypes that you see with radiation. You have burns and blistering, and it will totally damage the normal function of the body. So the person will basically suffocate to death because the cells in the lungs will just start to blister and fill up with water.
Why do they call it mustard gas?
Why? I don't know. Maybe it's the color yellow? I'm not sure. I never looked into that. Anybody knows?
I think it's because it looks like mustard. It's yellow.
Yeah, because it's yellow. I think I read it somewhere in my past life, but I don't remember it right now. I think it's because it looks like mustard.
Is that what the YouTube link is for?
Sorry?
Is that what the YouTube link is for?
Yes, if you want to see some drastic images of World War I and what mustard gas does. Oh, no, actually the link here, yeah, I was going to put a link for the World War I mustard gas usage, but I think those links everybody's probably very familiar with. So I put a link here on a current chemical attack on unsuspecting populations. Now, with the causes, as I mentioned, of the intercalating agents, it will distort the structure. It's going to go in the middle of the DNA and distort the structure, and that will cause insertions or deletions. And again, here, example, I have actinium bromide. It will cause gene mutation. UV light, another big one. As I mentioned, UV light will cause a radiation energy. It will cause deamination, depurination, cutting out the purine, right? And it will also cause thymine dimers. So what that means, remember, this is a ring structure that has an electron cloud both on top and on the bottom. You had double bonds followed by single bonds, and they're all in the same system. When you irradiate this with UV light, some of the electrons are going to attack the base that is under it. So you form these covalent bonds here that now cause a problem to the DNA structure. So other causes of induced mutation, as I mentioned before, almost the whole class last time, is ionizing radiation. You have electromagnetic radiation with also shorter wavelengths. You have also X-rays, gamma rays, cosmic rays. Do you know we are under a lot of cosmic ray bombardment every day? If it directly breaks phosphodiester bonds in the DNA, it will cause those very characteristic types of DNA damage.
Okay.
Now, there's another question here. Why do you treat tumors with X-rays? Colon cancers, commonly treated with X-rays, right? And then if it is a colon cancer in a man, that you have added problem because usually the colon is close to every other gamete form that you can imagine. So you have at the same time you destroy the part of the colon cancer, you destroy prostate gland, you destroy everything else that is on the way. Good to kill cancer cells, but bad for killing other cells as well. Other causes that can induce damage in DNA, viruses. As we mentioned before, HIV is one form of virus that you can think as a transposon. It gets in the cell and inserts itself into the genome and it doesn't come out. So that is DNA damage. Now, keep in mind that when you have a virus, a retrovirus that goes into the cell and it gets stuck into the chromosome and it doesn't come out, that's a form of damage that cannot be repaired. We don't know how to just get rid of the virus. Once it's in the cell, that's it. It doesn't come out. Once in the DNA, it's there for life. And the same thing happens with herpes virus. We can always control the symptoms of a herpes outbreak, but you can never quite get rid of the herpes virus because it's inside your DNA now. It's part of your body. HIV, herpes, and many, many other viruses that do that. Yeah, viruses very often cause cancer. Yeah. Now, how do you test if something is carcinogenic or not? How do you know if something is safe for consumption or not? One of the tests that you can do is called the Ames test. And this is very important to know because this is one of the few things that you can do to test for DNA mutation. This test came up around 1975. Now, how do you do this test? First, you get a strain of bacteria that cannot produce histidine. So it's a histidine knockout, cannot produce histidine. Now, you get it together with the chemical, just put some of the chemical there. Let's say you're testing sweet and low. So you put some grains of sweet and low in there. And then, of course, in order to test a chemical, you always have to compare it with something that does not cause a mutation. For example, water or a buffer of some type. So let's say here you have your chemical in one flask, you have your control in another flask. Now you put, after you grow this bacteria in this, with this chemical present, you put it in a plate that does not contain histidine. Now why? I just said that bacteria cannot grow in the absence of histidine. So why are you putting in a plate that doesn't have histidine? The bacteria needs it to grow. No, you put it there because if this chemical caused the mutation or severe mutations in the bacteria DNA, eventually it will cause some gain of function. And that will mean that now, before the bacteria could not produce histidine, but because of the mutation, now it can. So it will survive even if it does not have histidine in the environment. Now this part is very important to grasp. Okay, this is the basic concept of this Ames test. What would happen now if you compare the numbers of the one that caused the mutation with the ones that were spontaneously mutated? If it causes mutations, there's going to be a lot more bacteria growing in there. Now there is a problem with this. Okay. Now there is a problem with this Ames test because it's testing the chemical in bacteria. Now we are far away from the bacteria, I mean as bodies. So whatever works on the bacteria here may not be seen as a carcinogenic in an animal. So after this Ames test, other tests were developed, and then you have tests in mice, tests in rabbits, in dogs, in cats, and pigs, and monkeys, you name it. But eventually, if this drug will pass all of the tests, it will be allowed to be tested in humans.